This time I will discuss a rectangular footing design. The problem 12.15 in your book, it is saying design a footing with one side limited to 7 feet for the following. 12 means by 12 means edge column. Edge means like at the like boundary of the plan. Dead load given 130 keep, live load 155 keep, F prime C 3000 psi, Fy yield strength of reinforcement 60,000 psi, allowable soil pressure is 4 ksf, a distance from top of the backfield to bottom of footing is 4 feet. Now, now, the problem did not tell us it is a rectangular footing or a square footing. Typically, when you design a footing, you do not know whether it is square or rectangular. At the beginning, we will always try to make it square because square footing is better. It is stable like equally both ways. So we do not like rectangular footing. But sometimes due to the boundary line or availability of the land, sometimes we cannot provide square footing. Even for combined footing also, uh, sometimes we may need to provide combined footing, several footing together. So in this problem, you can see there's a limitation. The one side limited to 7 feet. That means one side of the footing cannot exceed 7 feet, maybe due to the boundary line. Uh, yeah, that is the most common cases. You can see here, this is a S column. In the S column, the boundary may be a problem. Maybe this is why it is a 7 feet. Whatever the reason is, so we will solve how to design this beam. Oh, sorry, no, not beam. It's a column. So if I open the solution here, what what your book did at the beginning, they assumed 12 24-inch footing. Now how did they design? They design like based on their experience. When you will design it, you do not know what should be your footing depth, so you will start with a very like the most, like the best you can do. So make a guess so that it is very close, then come back to your original guess and revise it. So here your book assume 24-inch footing. D is 19.5. 19.5, that means the cover from center of the bar is 4.5 inch. Now why 4.5 inch? Because this is a rectangular footing. So what will happen, one bar will be here, other bar will be on top of this, other set of bar will be top of this. So they are considering D from here, uh, no, they are considering D from here to there, that is they are considering. So as there are two layers of reinforcement, and we need to provide at least 3 inches of clear cover. So 4.5 inch here to here, 4.5 inch is a good approximation. Or if we use 4.5 inch here, that will ensure that there is about 3 inch clear cover here. So that is why this time it is 4.5 inch. Now you saw that when you did the column did mm, wall footing design, that time you did not deduct 4.5, that time you deducted 3 inch because the other set of reinforcement was temperature. We do not consider or we do not need to care about D for temperature. Okay, so that is something like special in rectangular footing, or it is in square footing. Also we provide 4.5 inch. So if I go to a solution, so they provided 4.5 inch from the center of the bar. Then they are calculating the effective soil pressure, which is allowable soil pressure minus the concrete weight minus the soil weight. Here concrete is 24-inch divided by 12 to make it into foot, and then this is 150 pound per cubic feet. We know that the unit weight of reinforced concrete is typically 150 psi, and this 2 feet 24 by 12, it is 2 feet. This 2 feet is the soil depth, and 100 psf is a good approximation for soil pressure. Now, if I go back to this figure, you can see the depth is 4 feet, and we are assuming depth from here to there is 4 feet, 48 inch. So if we assume our footing depth 24, another 24 is here. So finally, we got 3500 psf. That is our effective soil pressure. So effective soil pressure means whatever soil can apply to my foundation minus the balance that my concrete and soil will reduce it. So okay, then we find the area required. A required means area of the footing. We determine the area of the footing based on service load divided by effective soil pressure. 130 is most probably our dead load. 155 is most probably our live load. We did not factor here. Okay, if I go back to your problem to check it, if you did not memorize, you can see dead load 130, live load 155. We did not factor it. The reason is when we design or when we determine the size, we take the service load. 3.5 is this 3.5 KSF. Because this is in keep, this should be in KSF. Then I'm getting 81.43 foot square. So we need this amount of area. We know that one size cannot exceed 7 feet, the problem said. Then the other side, if we use 11 feet 8 inch, the area is becoming 81.67 foot square. Now I need 81.43. I am providing 81.67. So I am providing slightly more, which is good. I cannot provide less. I can provide more. Now you can provide here 12 feet to make it a round number, no problem. But at it is an is column, boundary line may be a problem. So this is why the solution is becoming very like careful. They are not giving more than whatever is needed. Okay, but you can provide here 12 feet to make it a round number. Your field labor or site engineer, they will love the round number. Okay, now we will do the ultimate load, or is the factored load. Yes, so 1.2 dead load plus 1.6 live load divided by the area you are providing, then this pressure will be your ultimate bearing pressure. In technical term, we call ultimate bearing pressure. That means the factored pressure. Okay, so size is based on service load, but the shared design and reinforcement design will be based on factor load. That is the design specification for ultimate strength design method. So first, now we will do one-way shear. So we know where one-way shear is critical at d distance from the face of this column. D distance from face of this column. So this is my column at the distance from here. Now this time what they are doing, last time when we did square footing or wall footing, we assumed a 1 feet strip. We assumed a 1 feet strip here. This way we assumed a 1 feet strip. That way my B was 1 feet or 12 inches. This time they are assuming the full as their B. No problem. Whatever you assume, if we assume 1 feet is strip, that is also good. But they are assuming full 7 feet as their width. If you do that, no problem. Whatever the reinforcement or whatever the size will give it is the same thing. Okay, then what is this distance? This distance will be, what is my entire distance? If you can remember, 11 feet 8 inches. 11 feet 8 inches, that means full was or 11.67 by 2. If you do it, you will come at the middle of this column. Then deduct the half of the column, which is 6 inches. Divide by 12 to make it into feet. Minus here to here 19.5 inch. Why? Because this is our D. So D is 19.5 divided by 12. That will be in feet. So hopefully you understood how they got it. Then how did they calculated the shear force? The ultimate pressure times this, then it will be keep per feet this way. Then times this, you can see times this become keep 128.4 keep is your um, one-way shear. Now if we assume a 1 feet strip, your B would be not 7 feet, it will be only 1 feet. That is also good. In that case, you will get your shear force for 1 feet strip. Okay, then what is the depth required? We will, we know that there will be no tie or stirrup to take the shear force. Only the concrete will take the shear force. So we know that the capacity of concrete is uh, B is like P 2 square root F prime C B. D. That is the capacity of plain concrete. So as we are calculating D, we took D this way. So shear force divided by this. This is P 0.75. 2 is to square root F prime C 3000. That is the concrete strength, and that is the B. Now, as we are assuming 7 feet total, our B is 84. If we assumed a strip here, if we assumed a strip here, 1 feet strip, then we would use 12 here. So you can see, as we are assuming 7 feet here, our shear force is huge because a larger area. If we use one here, it will be less. At the second time, you will divide by less. So ultimate result is same. Okay, so our D required by calculation is coming 18.61 inch. We are providing 19.5 inch. That means we are providing slightly more, which is good. If there is huge gap between these two, that means we need say 8 inch. We are providing 19. That means it will be over design. We will go back at the beginning and revise our section. Okay, but before going back, we should check our two-way shear. Two-way shear means punching shear. We know that we discussed it from earlier that our square footing, rectangular footing, there might be some punching problem, and punching problem occurs at d distance from the face, d distance this way. So what is here to here? Column size plus d by 2 plus d by 2, or simply d by 2, d by 2 is simply d. So column size 12 means plus d is 31. Now this 12 is the column size, and this dimension is column size plus d is 31.5. Now what is our perimeter? 4 times this. So 1, 2, 3, 4. 4 times this, that is our perimeter. Now what is the shear force? In last video for square footing, we discussed this. We can calculate shear force by taking entire area, entire rectangular area, minus this punched area, then we'll get the outside, the shaded region, times my effective soil, not effective, sorry, ultimate soil pressure, then we'll get it. You can see 81.67 is our entire area, and minus this 31.5, which is this dimension, divided by 12 to make it into feet square, because this is a square, this is a square, so the area is just dimension square. This 12 is just to make 31.5 inch to feet, then times my ultimate soil pressure 4.947. You saw that how did we calculate it? Based on the factored load. So we got our punch shear 369.4 keep. Now we know that there are two equations for punching shear capacity. One is this, punching shear is dp 4 square root a prime c b naught. B naught means the perimeter. Other equation is this equation, where this is punch shear, p is alpha s d b naught plus 2 square root a prime c b naught. So this equation, as we know our punch shear, we are punching shear, we are inserting here. We know phi 0.75, 4 is 4, 3000 psi, b naught 126. We just got it. Okay, after calculating, we are getting 17.87 is very close to our provided and less. That means we are good. In this equation, I discussed earlier that this equation, if we insert, this is d, we are insert, no, this is alpha s. Alpha s is 30, although it is not clear because your book made some mistake. They wrote 40 here, I wrote here 30. Now why 30? If I go back to the problem, it is saying, see, is column. For is column, alpha s is 30. For interior column, alpha s is 40. For corner column, alpha s is 20. So if I go back to solution, and this d, ideally this d and this d both are same, we should solve for d. But if you insert d here, and if you find a very like close number, then we will do that. If you find a number which is way away from my provided, then we will not do it. So at the beginning, to make it simple, we are inserting our d. 2 is 2, a prime c 3000, and here is b naught. After solving, we are getting 8. Now this calculation you may not get 8 because they used here 40 by mistake. So I wrote here 30. So you may get um, slightly larger number, say 9 inch, whatever. So we need 9 inch, and we are providing 19.5. So there's a huge gap. So I do not need to revise this calculation. Whatever I use 19 here, if I use now, if I use a d here and solve for d, that will be a very close number. And we should not play and precisely with non-precise value. Whatever the actual number is, this will not win because see, I am providing 19. This one is saying I need 17. If I see the one way share, it is telling 18.61. So obviously this one is controlling. I need actually 18.61. I am providing 19. So shared design is good. Whatever depth we assume 24 inch is good. We do not need to go back and revise. If we find here that oh no, our section is not good, we have to go back at this point. And also in your exam, if the problem says design for shear only, then our design is done only. Design for shear means select a depth that will work for us. So shared design is done. That means whatever we assume it is good. Now we will do reinforcement design. First, longitudinal reinforcement. Longitudinal reinforcement means our column is now rectangular. That means this is our not column, sorry, footing. This is 7 feet. This is 11 feet 8 inch. Our column is here. We will design for longitudinal reinforcement. So how to calculate the moment? Moment is critical at this phase. So we will design it as actually a cantilever beam. So this is our phase. Moment is critical. We will calculate this distance and we'll calculate the moment here. If this is QU, then our moment will be QUL square divided by 2. This L means this L. Okay, so we will see. Let us go to the point. So if I go to your book, see first they calculated lever arm. What is that? The L I was talking about. 11.67 by 2, then you will come to the middle of the column minus the half of the column. Half of the column is 6 inch divided by 12 to make it into feet. This is feet, so 5.33 feet. And they calculated moment Q L L by 2. Now why they are doing 7? Because they are considering the entire, they are considering, because you can remember this QU is KSF. So if you multiply by 7, you will get load this way, keep per feet. Load this way, keep per feet. This is where they are doing it. And if I, the half of the column is 11.67 divided by 2 minus I have 6 inch here. That is why that is how they calculated L. Okay, so we will go back to the solution. So hopefully you will understood how to calculate moment. Do not make this mistake 7 because we are assuming the entire width as my B. Now you can assume here 1. 1 means 1 feet. 1 feet is strip. Then whatever the reinforcement you'll get is for 1 feet. Then you will copy paste in the entire width. So to explain that better, that means this is your footing. You can assume a 1 feet strip. If you use 1 feet strip, no problem, it is okay. Then whatever reinforcement you will get, then you will copy paste all over it. that is also okay. But in this problem, your problem is assuming 7 feet as your width. So no problem, if you multiply 7, your moment will be higher, your reinforcement will be higher, but you'll distribute it along the entire width, so no problem. We know our moment, we know our size, so we do this way. Mu over phi bd square, we calculated. You can remember this equation use pound inch. So they multiply 12 to make it inch, they multiply 1000 to make it pound. Then divide by zero point 0.9 b. You can see here, if we assume 1 feet is strip, this would be 12. You're assuming entire 7 feet, so this is why 7. So no matter whether you are using 1 feet or the entire, it is the result is same, just you will have to careful what you are doing. D square, we know it, we got 205.6. Then we'll go to a table to find our row. This time table A12. Why A12? Because our A prime C is 3000 KSI, Fy is 60,000. For that we need appendix table A12. So we found row is 0.0034358. Now we have to check whether this row is more than the minimum or less than the minimum. So hopefully it is more than the minimum and less than the maximum. You can go to table A7 to verify that. Based on my memory, I can verify that lowest was most probably 0.0018, no, 0.0033 most probably, and the maximum was 0.018. Most probably yes. If I'm wrong, just check it, yes. But I know this is more than minimum, less than maximum. So reinforcement is row B D, and we got 5.86 inches square. Now this reinforcement is for the entire width, and they are assuming 8 number 8 bar 6.28, very close, so it's okay. And spacing 84 inches is my width, they are deducting 2 3.5. What is this? It is the uh, clear cover from the center of the bar. Okay, so if I go back to a figure, how did they calculate? If I go here, so this is my foundation. So one reinforcement will be here, one reinforcement will be there. They are deducting here 3.5 inch from the center, and here 3.5 inch from the center. Now how, so total is 84. So total you had 84, you are deducting 3.5 both side, and your reinforcement will be 8 number 9. So 2 3 4 5, 1 2 3 4 5 6 7 8. So 8 bar. So 1 spacing, 2 spacing, 3 spacing, 4 5 6. Did I make any mistake? So one spacing here, 1 2 3 4 5 6 7 bar, so 8 bar. So another 7, so 7 spacing divided by 7, you will get center to center spacing of the bar. Why do we need to check it? Because we should make sure that the gap between the bar is at least 8 inch or bar diameter, and the maximum spacing cannot exceed 18 inch or 3 times the age. So this should not be a problem, because we know that there's no scope for that, but there might be some scope, we should check it. Number one. Number two, we should tell the field labor also that what will be the spacing of this bar, like this 8 number 8 at the rate of, we should tell the spacing clearly. Okay, so we'll go back. If I go back to problem, they found 11 inch center to spacing. That means good, more than the minimum, less than the maximum. Now they are checking the development length. Now by this time, if you know what is development length, in another video I told about it. If you know it, you can check it. If you do not know at this point, then you can skip this portion. But I'm discussing very briefly what is this. This is, so our footing is this. You say this is our long side, long size feet. Now our maximum moment is here. So when we will provide our reinforcement here, we should make sure that we have at least the development length, so that the anchoring force here is developed to carry the force here. Now, so you should calculate development length, and I discuss how to calculate development length is another video. It is this equation: lambda f prime c psi t psi e psi s divided by cb k tr divided by diameter of the bar times the diameter of the bar. So this way you have to calculate your development length. Now you should make sure that you have that space. Now, if you do not have an space, what to do? You can do a hook, or you can do a 180-degree hook, or you can. There are so many alternative, but mostly it will be okay. If it is not okay, you can make hook, and that hook should be able to do it. Now that is the checking here. So that development length calculation they are checking here, and I discussed this parameter in this video. It's very simple, clear cut. I'm not discussing the development length here because it will be so lengthy, because this is another discussion. It takes time, but simple, nothing clear. If you go back to there and you can check it. But just very briefly, after calculating, they found the development length required is 26 inch, or say 27. Now, do you have that space? Come here and to see. You can remember what is the distance here. The distance here was uh, uh, 11.67 divided by 12 feet. You'll come to the center. Minus 6 inch. Minus 6 inch divided by 12 is your feet. You should deduct some spacing here, because there should be some clear. Say that clear is 3 inch divided by 12. Whatever, what is available. So if I go to the solution, it is saying available is 61 inch. At first they wrote 64 because they forgot the clear 3 inch. I wrote here 3 inch and made it 61 1 inch. So roughly they have 61 inch and they need only 27. So there is sufficient length to cover the development length. So development length is not a problem. It is done. Okay. If it is not okay, they should check with hook. They can make hook, and in that case they need less distance. Okay, so we will go back, sorry, we'll go forward. Now we will design reinforcement for short direction. Now, when we design footing for square, both direction, it was same. Now it will be different. Why? Because one side is long, one side is short. So if I go back to the sketch, so my column footing was this, my foundation is here. Now we will design reinforcement this way. This way. So if I take this push this side as my beam, my beam will be this way. So now our reinforcement moment is critical at face, and we should calculate this distance. This distance is here to here, this distance. So we are designing this way, because this way versus this way is not same. So we should check this way. Now this portion we did not do in square footing, we need to do in rectangular footing. So they calculated 7 by 2, you understood why it is 7 by 2 if I go back, because whole is 7 feet by 2 is coming at the middle, minus the column width 6 inch, you'll get your this distance, or here to here. So if I go come to your point, yes, so 6 by 12 is 3 feet. So reinforcement moment is um, the ultimate bearing pressure L by 2 times your width. Now your width, can you remember what is your width? If I go back, your width should be, this should be your entire width, 140 inch, or 11 feet 8 inch. This should be your width. Now you can consider a 1 feet strip, no problem, and whatever reinforcement you'll get here, you'll copy paste all over, copy paste. You can do that, but it's a good idea to do it the entire width. And there is a reason, because for rectangular footing in short direction we have some other story, we will tell that. So it is a good idea to determine the reinforcement for entire width. So they used 140. Okay, so if I come So here you should use 140, 140 or the entire width, which is not 7 feet this time. The longitudinal dimension 11 feet 8 is, so 140 here. So, oh, 140, that is in inch. You have to divide it by 12. Mm, let me make sure. This load is in, it is in feet. This is in Ka7 feet. Yes, so this should be in feet. So 11.67 feet. It should be in feet. Then you are getting to 59 cubic feet. Then let us find mu over pbt square. It must be in pound inch unit. So that they multiply by 12 to make it in inch. They multiplied by 1000 to make it pound. Divided by zero point 0.9. Now see B is 140 inch. 11.67 feet. No, we use here inch. Divided by d square is 65. Now they should go to the table A12, most probably appendix A12, to find our row. Now you have to say this row should be more than the minimum and less than the maximum, and minimum was 0.0033. So it is less than the minimum, so they cannot take minimum. They have to take the, and they cannot take less than minimum. They have to take the minimum. So they took this value 0.0035. Then B D. This time B is 140 because we are doing short direction, or B will be the long direction. So 140. So they need 9.10 inch square. This reinforcement is for entire width, and say it is 16 number 7. They are choosing 16 number 7. They are providing 9.6, very close. Now 16 9 7. There is some story here how to distribute it. So if I go back, so for now if I make it bigger, for longitudinal reinforcement we distributed uniformly. 8 bar, 1 2 3 4 5 6 7, 8 bar we distributed uniformly. My column is here. For short bar, so when this side will bend and this side will bend, the most bending will be in the center or square portion, that is called bandwidth. Bandwidth. Hopefully you understood. When this side and this side will bend upward, the most bending will be in this region, bandwidth. So when we'll provide the short reinforcement, how many, if I can remember, hopefully 16 bar, yes, 16 number 7. So 16 number 7, what we'll do, we will provide most of the bar in this region, and some bar here, less bar here. How much here? That is that calculation. That is something new to rectangular footing. It was not in the square footing. So if I go to the solution, so reinforcement in bandwidth divided by total reinforcement in short direction. 2 divided by beta plus 1. This is beta. Beta means the ratio of the long side by short side. Long side is 11.67, short side is 7. So this is beta. After calculating, they found 0.75. So if they move this portion that way, so reinforcement in bandwidth will be 0.75 times the total reinforcement. Total is how? 16 bar. So 16 bar, so roughly they are getting 12 bar. So they will place 12 bar in the bandwidth and the other 4 bar in the outer side. So what they are doing, mm, so 12 bar, total is 16, 4 bars are remaining. What they assume, 2 number 6 bar in on center outside. I don't know why it is number 6 bar. It should be number 7 bar because total is 16 number 7. So this should be number 7 bar. I do not know why they are telling 6 bar. Maybe it is a mistake. It should be number 7. Okay, so if I go back, so this portion 7 feet, this portion 11.6. So the reinforcement in this portion will be 2 divided by 11.67 divided by 7 plus 2. times the total is number 11, so 6 12 bar. So 12 bar will be here, in this region, 12 bar, another 2 here, another 2 here. That is the reinforcement distribution. If I write here this way, not 12 number 7 bar. If I do here 1 and there 2 number 7, if I do here 2 number 7. Now you have to calculate the spacing, because you have to check the minimum spacing and maximum spacing. Here also you have to check the spacing. So it will take time to check it. And also you have to consider the development length. What is that? So if I go back, there, so let us take a new. Okay, so we know that our maximum in short direction. See the reinforcement here, the maximum moment is here. I need to make sure I have this development length in this way, and same thing I have to check I have development length in this way. If I do not have it, then I can hook the bar. So we should check it, and that is why they calculated the development length here. After calculating, they found 24 inch. How much space do I have? 33. How? 7 feet, that means 84 inch, divided by 12, that means at the middle, minus half of the column, minus 3 inch clear, total is 33. If I go back here, how they got it? This is 84 inch, divided by 12, that means at the middle, minus 6 inch, and then some spacing here, because I will not extend by my more than this. I will leave some clear here. So 84 divided by 2, 66 inch minus 3 inch. They have 33 inch, and they need LD 24 inch. So yes, they have a space. They do not need to make any hook. Okay, so design is done. Then what we need to do? We need to give them a like clear sketch. So first say long side. Long side you have to show in a clear. Okay, this reinforce. So this is 11.67 feet. You have to show this bar, and then the other bar will be. mm, okay, maybe you do not need to show long space, because you can show directly. So this is 48, this is 24. You have to show clearly. Reinforcement here, this is your bandwidth. So 1 2 3 4 5 6 7 8 9 12. One bar, two bar, one bar, two bar. So this longitudinal bar, I forgot how many bar. So this was 12 by 12 inch column. Longitudinal bar I forgot. Okay, let me go back and check. Longitudinal bar, if I go back, it was 8 number 8. So this will be 8 number 8 at the rate of what was the spacing? You have to tell the spacing also. Same thing, you have to calculate this spacing also. This is say 12 number 7 bar at the rate of, you have to tell the center to center, or sometimes we call one center, whatever you call one center. And same thing we have to tell this way, 2 number 7 bar at the rate of, you have to calculate the spacing here. There are some work here. Okay, so I will stop here, because my video is becoming so long. You may not watch it. So hopefully you are understood what I mean. You have to tell the reinforcement clearly in net sketches, so that field labor or field engineer can identify or can understand very easily. You cannot keep anything vague. Okay, so I will stop here. In the next video we'll see something else. Thank you.